All right, welcome to Concept A, which is our first lesson in Unit 1 this year in chemistry. We're going to be talking to concepts related to the terms accuracy and precision. So hopefully by the end of this lesson, you'll start to get the basics of differentiating between accuracy and precision, the terms, and then you'll also be able to perform percent error calculations. So I'm going to give you just some real-life examples, so you don't need to write this into your notes, but what is the difference between these terms, accuracy and precision? So a group of people were asked to estimate Ellen DeGeneres' age, and you can see the 6 responses on your screen. Now, accuracy is how close you are to the actual value. So in this case, we are concerned with Ellen DeGeneres' actual age. So this year that I'm recording, Ellen DeGeneres is actually 56. So which response was most and then which one was least accurate? So out of our 6 responses, and again, we're comparing these to the age of 56, the guess that was 58 was the most accurate, and the least accurate was the one that was 32. So again, accuracy is concerned with the actual value. In reference to precision, we asked 3 sets of friends to estimate Olympian Ryan Lochte's age, and you can see the 3 sets on your screen. Now, precision is how consistent a series of values are with each other. We're not actually concerned with the Olympian's actual age. So if we look at each of the groups, which one is the most precise would be group 3. Those 4 values within group 3 are the closest to each other and considered most consistent. So the definitions I do want you to get into your notes are on your screen. Accuracy is how close the experimental results are to the true or real value for the quantity being measured. That's what you should be writing down. You can put it into your own words as well. This also can mean, another way to explain is that the smaller the difference between the measurement and the accepted value, the more accurate that measurement is considered. The definition for precision is how well a measurement can be reproduced if the same is measured multiple times. And again, you can place that into your own words. You can also be explained in terms of the smaller the difference between the reproduced measurements, the more precise the measurements are. All right, so this bullseye diagram is a very common tool for explaining accuracy and precision. So if you look at the diagram, you can see the 5 darts are very close together, but they're not at the center where the bullseye is, which is the goal of shooting at a dartboard. So this set of 5 darts represents precision, but that it's inaccurate. The next set of 5 darts that were thrown are very close to the bullseye, however they're spread out from each other. So this is an example of an accurate yet imprecise situation. And finally, you can see those 5 darts were able to get closer together on that bullseye. So this is an accurate and precise diagram. All right, so percent error calculations evaluate accuracy. This is going to help us tell how close our measurements are in the lab to our accepted values for the same types of measurements. So 2 important terms that you have to be able to differentiate between while problem solving and working in the lab is that our measured value is the one that's experimentally determined. This is the value you actually get from doing the lab yourself. Our accepted value is the most probable value of the measurement, usually given to you by your teacher or found in a reference table or text. So here's our formula, the measured value minus the accepted value over the accepted value times 100. This formula is on the back of your reference table. So I expect you, especially in the first quarter, to be looking it up, making sure you have everything placed where it needs to go. One little piece of information in terms of a percent error, and especially this pertains to any of the honor students, is that accurate is usually seen as having a 5% error from the expected value. We can also use a percent error value to evaluate precision. Trials are considered precise if they have a percent error range within 10% of each other. So we'll kind of go into this a little bit more when we actually get into a lab, but really being able to get 5% or less is definitely a success in terms of our accuracy and precision in the lab. All right, so percent error problems we're going to go through and you're going to try one out. The big thing is showing your work this year, and we'll kind of go over some of the math rules at the end of this. So in your modeled problem, and you can read through this, we have a student that's measuring mass and volume, and they're calculating the density. Well, according to his results, copper has a density of 8.37. However, he consults a reference table and finds that the accepted value for density is 8.92 grams per centimeters cubed. So what is the student's percent error? Over here, I've just listed some knowns and unknowns, just so you can kind of pull out the information. This is a pretty wordy problem, so we're just going to pull out the two values and recognize that the student's measured value is 8.37, and then the one from the reference table is our accepted value of 8.92. So here's my formula. You can see I've shortened measure value to NV, accepted value to AV. I'm going to plug in my values and then solve for the percent, which is 6.17%. Okay, our practice problem, I would say if you understand how to use the equation, I would just pause it and then you can check back to see if you set it up and got the correct answer. So here, aluminum was found in the lab to have a specific heat of 0.156 calories per grams degrees Celsius, but the actual value was 0.185 calories per grams degrees Celsius. What is the percent error? Measure value was the first one in this case listed of the 0.156. Accepted value was the 0.185. Setting up and showing the equation, plugging in the values correctly, especially being careful that you always put the accepted value in the denominator, and then solving for 15.7%. All right, so that's all set for the percent error calculation. Just a couple of important math rules to remember this year. Dress your numbers. All measurements and answers to math problems should have units written after the numbers. That way you're always kind of having to go back, making sure that you're setting things up correctly, and that we don't just find a number somewhere on the page, that there's meaning behind it by knowing what the number goes with in terms of units. And like I kind of mentioned in the beginning of the percent error calculations, you need to be showing your work. You should be showing me the equations, you should be showing me how they're rearranged, inserting in your known values, and in the final answer rounded properly, and we'll eventually get into significant figures with units after. All right, well that's it for this very first lesson. Make sure go back through your notes, make sure you don't have any questions. If you do, jot them down and we'll go over them first thing tomorrow. I'll leave you with a little cartoon that one accurate measurement is worth 1,000 expert opinions.